In the past lectures, we had seen, given a linear system represented in the state space form of x not equal to x plus du and y equal to cx plus du, where x, y, and u are real vectors, and a, b, c, d are real matrices, and they can very well be time varying. So, given an input ut, how the solution trajectory for the state xt will be, and what would be the corresponding yt. Okay. The same state space representation can be expressed in the block diagram form as shown here. In this lecture, what we will be discussing is two concepts that are associated with linear systems, which basically try to identify the following. If I am given a time interval, let's say from t0 to tf, where t0 is considered to be the initial time and tf is considered to be the final time in this particular time interval, and suppose I am at some state x of t0, is it possible to find a continuous input u, continuous time input u, such that the solution trajectory, which is x of t, or the solution to this state vector x of t, starting from the initial state x of t0, which is, let's say, x0 in this case, will pass through a point xf in time tf. Okay, can I find a ut for those points or not? Okay, so I'll repeat this. Suppose we have a time interval t0 to tf, and suppose we are starting at a point x0, or x of t0 being equal to x0, and we want our solution trajectory of xt to pass through a point, let's say xf, at the time t equal to tf. The question is, will there exist a continuous time input such that this happens? Okay, solution trajectory starting at xt0 passes through a point xtf. Okay, please note that the trajectory will pass through the point, but is not going to stay at that particular point at any finite time t. Okay, so we will consider a linear system which is of this form, where a, b, c, d can very well be time varying. X is a state vector, it's a real state vector, so we are considering nth order system here, so it belongs to Rn. There are n inputs and p outputs, all of them being real. So, in the context of this discussion, we will see what is reachability, basically how far can we reach, or what are the points that we can reach, and what is controllability. Okay. So, reachability essentially tries to see if you initialize your state from the origin, what are the points that can be reached in a given time interval for some continuous input. Okay. Simply put it is this: the initial condition states that the system is at origin, which means x of t0 is essentially 0. We have been given a time interval t0 to tf. We want to see all those points through which a possible solution trajectory of x can pass through for a suitable input u. Now, this input, continuous time input u that you select, will of course be different for different inputs, possibly different for different final states that we are considering, or the states through which it should pass at time t equal to tf. Okay, so basically so from the initial state xt0 equal to 0, given the time interval t0 till tf, t0 is the initial time and tf is the final time for this interval under consideration, we want to see which all states can be reached Okay, or the solution trajectory of x of t can possibly pass through which of these states at time t equal to tf for some corresponding continuous time input ut. Now this continuous time ut may be very well different for different solution trajectories that you are generating. But all the solution trajectories are going to start at 0, and depending on the control input, they will pass through certain points at t equal to t. So whatever admissible inputs that you can, whatever admissible continuous time inputs that you can consider for this system, once they are applied, at tf we'll see through which the trajectories are passing, through which points or through which states the trajectories are passing, and those states are basically something that we say that can be reached once you start from the origin. Okay, so we consider this set of states that can be reached from the origin for a suitable continuous time control input as the reachable space. On the contrary, controllability says if you start from any non-zero state, if the initial condition is from any non-zero state, can you find a continuous time input t0 till tf such that your trajectory passes through the origin at t equal to tf. Okay, now you take a collection of all those points from where a trajectory can originate and pass through the origin at t0 equal to tf for some corresponding continuous time input. All those initial states together form the controllable set, because you can control the state, control the behavior of the system so that it evolves from a non-zero state and passes through the zero state at some time t. Okay, at a given time tf. So to formally put what reachable set is the following. A state xf, okay, is said to be reachable if you are able to find a continuous time ut over the interval t0 to tf. The t0 is the initial time, tf is the final time, the finite time. Okay, tf is a finite value, such that xf satisfies this particular relationship. Now, as I said, for reachable state, we are considering the initial condition to be 0. So now if you recall from the solution, x of 0 being x0 being 0, we do not have the 0 input response part. Okay, so what you essentially seeing here is the 0 state response. Okay, so the 0 state response over a time interval from t0 till tf should be such that it reaches a state xf. Okay, that is why this relationship comes up. This is for some tf that is given to you in the interval t0 till infinity. So tf is essentially a finite time given and it is greater than t0. Okay, so to simply put, the state is transferred from a 0 state to a xf. Through some control input ut, and this control input is a continuous time control input. Now the set of all these points which can be reached from the origin is known as the reachable set. Okay, so all those points in the Rn space are considered to be reachable if you can find the input corresponding to that point such that the 0 input response starting from t0 ending at tf takes the solution trajectory to xf. Okay, this holds. So this is how the reachable set is defined. You can reach the state at a time t equal to tf starting from origin. Now what is this control input? One such control input that can be thought of is this. Ut is B transpose phi A transpose TFT psi F. Okay. Psi F is some vector in Rn, some arbitrary vector in Rn. Okay. Ut is this. So if you substitute this, what you get? Substitute this where? Substitute it in the expression or the zero state response expression for XF, because XF is considered to be a reachable point. So what we are trying to see is, if XF is a reachable point, what can be a possible corresponding control input? The possible corresponding control input can be this B transpose phi transpose psi F. So if you substitute this, what you get is XF to be integration of a product of matrices multiplied with psi F. Okay. So this integration of product of matrices results in n cross n matrix, and this matrix acts upon psi F to basically give you the state XF. Okay. Now everything inside this bracket that you see is known as the reachability Gramian. Okay, and is denoted by WR T03TF. So the subscript R indicates that it's the reachability Gramian, and T03TF denotes the interval over which the reachability Gramian has been evaluated. Okay, so WR T03TF, as I said, if you note, is of the size n cross n. Okay, we can verify. Phi is going to be of the size n cross n. B is of the size n cross m. B transpose is of the size m cross n, and phi A transpose is of the size n cross n. So the product of this and taken an integration of that is going to be n cross n. The product of phi B, B transpose, phi transpose integrated over T0 till Tf gives you the reachability Gramian. So what you see here is XF is nothing but the product of this n cross n matrix, reachability Gramian, and psi F. So XF is said to be lying in the image space of this reachability Gramian, because the reachability Gramian is a square matrix that takes a vector psi F and maps it to XF. Okay, so the Rn is considered to be the domain and XF is the image space. Okay, so if XF is a reachable set, then it has to lie in the image space of the reachability Gramian. That is what it looks like. Now, what do you mean, or what one means when a system is said to be reachable? A system is reachable if the reachable set is equal to the entire Rn space. This essentially means that if you start from origin, then you can reach each and every point in the Rn space, and for in the given time interval T0 till Tf. You are given one time interval T0 till Tf. If you start from origin at T equal to T0, you can reach every other point in this particular Rn space within this particular time interval of T0 till Tf. And for each of this, there would be a suitable continuous time control input. If this is the case, then the system is said to be reachable. So the reachable set is essentially the entire Rn space. Okay. So this is what reachability of a system means. So you should be able to reach all possible states within a finite time interval with a corresponding continuous time control input if you start from a zero initial condition. Now we will proceed to the next concept, which is basically controllability, which essentially is trying to see, if you start from a non-zero initial state, can you find a control input so that it takes you to the zero state in a given time interval T0 to T. Okay. So a state x0, purposefully labeled it as x, it has been labeled as x0 because this is going to be the initial state. A state x0 is said to be controllable if you can find a continuous time control input over the interval t0 till tf such that the state trajectory starting from time t0 at the initial state x0 under the control input over the time interval t0 till tf reaches the zero state at t equal to tf. Okay, and this tf is a finite number that is given to you. Okay, finite time that is given to you, which is greater than t0. So basically what we are trying to see is, can a state, non-zero initial state, be transferred to the zero state from in the time interval t0 till tf. So you should be reaching the zero initial state at t equal to tf. Okay, for this you should have some continuous time control input available to you. So the set of all those points for which there exists a control input that can transfer the state from x0 to 0 at t equal to tf is known as the controllable set. Okay, so that is what has been formally put here. So x0 belonging to Rn such that there exists a control input which satisfies that the solution trajectory at t equal to tf starting from x0 should be 0. Now what is this control input? It is this. This is one such control input. The control input is minus b transpose phi transpose xi0. So xi0 is some vector in Rn. Okay. So if you notice, there is some similar looking structure with respect to the control input of the reachables, control input for reachability, or the reachable set, and the control input for the controllable set. Is this? There you had a b transpose phi transpose psi f. Here you have a b transpose phi transpose xi0. However, the difference is the phi was basically a function of tf and t for the case of control input regarding reachability, whereas here the phi is a what should I say? Is a function of t0 and t, the initial time, for the case where control input is going to find, so that x0 is a controllable time. Okay. So now if you notice, if you substitute everything here, we get x0 to be equal to this right hand side expression. So you have the product of matrices integrated over t0 to tf, and this entire thing is multiplied by this vector from Rn, the xi0 vector from Rn. So everything inside this bracket is known as a controllability gradient, denoted by Wc. So C represents the controllability gradient, and the bracket entries in the bracket which is t0 till tf essentially indicate that the controllability gradient has been evaluated in the time interval t0 till tf. Now again, if you observe, x0 is nothing but the matrix Wc multiplied by y0. So x0 lies in the image space of this matrix Wc. Okay, so x0 is in the image space of Wc. Now, for a system to be controllable, similar for a system to be reachable, you need the reachable set to be the entire Rn. If you want a system to be controllable, then you have to establish, or rather, if a system is said to be controllable, then it means the controllable set is essentially the entire Rn space, which indicates that no matter where you start, given a time interval t0 to tf, for every initial condition, you will be able to find a corresponding continuous time control input such that your initial state is transferred to origin at t equal to tf. Okay. So now the question comes, how do you check reachability and controllability for a given system? Okay. So before we proceed, I put you put this question to you. Prove that the reachable set that we just saw for a linear system and the controllable set for a linear system are essentially subspaces. Subspaces of what? Subspaces of Rn. Okay. Essentially the space over which the states are Rn. Now, why do we need to study this reachability and controllability? So, as we proceed further with this concept of reachability and controllability, there are two things that will become clear. One is for a linear system, if something is reachable, if a linear system is reachable, then it implies that it is controllable, and if it is controllable, it implies reachable. Second, if we are able to prove that a system is controllable, then it means that we can design a feedback control so that we can make the system behave in a stable form. Okay. If something is controllable, then it means that it is possible to design a closed loop system with a feedback such that the closed loop system is going to be stable irrespective of whether the open loop system was stable or not. So we'll stop here. Thank you.